All right, so today we're going to be looking at images in concave mirrors. Okay, the first thing we're going to look at concave and then convex, but we're going to focus right now on concave. And a concave mirror is really just a mirror whose reflecting surface curves inwards. Okay, it forms kind of a C. So say if you were standing right here, the mirror face would be right here. Okay, sometimes these mirrors are called converging mirrors because what happens is all the light rays from infinity, right? Remember how the sun can release infinity light rays, okay? The infinity light rays that are released by an object or that are reflected off an object or illuminated from a luminous source are coming at the mirror and they all converge at one specific point, okay? This is the diagram of what a concave mirror would actually look like in real life. Okay, these are obviously the ray lights, incident ray reflected down to the focus. And we'll learn about the focus in a second. This is what the optics or the scientific symbol would look like. Okay, it's just a semicircle inward with your opaque side on the bottom here marked off by these hash marks. The exact same as a plane mirror. With a plane mirror, we just had a flat surface. This time we're looking at a curved surface. And again, this is concave. Okay, so the reflective surface forms a backward C this way. Okay, and they all converge inside. Some terminology that we're going to need to know for both concave and convex mirrors. The first thing is your center of curvature. Your center of curvature is the center of the sphere whose surface has been used to make a mirror. Okay, your center of curvature is like the radius. So pretend this mirror went around in a full circle. Okay, this would be the center of that circle. Okay, you also have your principal axis. Your principal axis is this line right here. Okay, that's the one line right there. It goes to the middle of the mirror where your vertex would be. Your vertex is where your principal axis meets the mirror at a 90-degree angle. Okay, vertex. So we have your principal axis is a line through the center of the curvature to the midpoint of the mirror. So line of center of curvature to the midpoint of the mirror. Then you have your vertex is the point where the principal axis meets the mirror at a 90 degree. I already talked about that. Okay, and then the point where the light rays parallel to the principal axis converge. Okay, so remember how I said you're looking at a concave mirror as a full circle. This would be the center of the sphere. Okay, and that is the center of curvature. Okay, the focus is the point at which where all the light rays that run parallel to the principal axis actually converge. Okay, so if I have a parallel ray here and a parallel ray here to the principal axis, what happens is that these points will always pass through the focus. It doesn't matter how far away from the principal axis I am. I could be right above the principal axis and hit here and it would go through here. I could be really high up above the principal axis and it would hit up here and still bend towards the focus. Okay, and that's why it's called a converging mirror, is because all of the rays that are coming parallel to the to the principal axis are actually going to pass through the focus. Okay, and the focus is really just half of the center of curvature. So if my center of curvature was, say, 20 centimeters away from the mirror, my focus would therefore be 10 centimeters. Okay, so it's half of the center of curvature. Okay, and the focus is where all the light rays that are coming from infinity, from way over here, okay, are going to bounce off, that run parallel to the to the principal axis, will bounce and reflect and converge. Okay, and that's why it's called a converging mirror. Okay, converge at the focus. So there are some basic rules when we're locating images in concave mirrors. The first one is a light ray parallel to the principal axis, or PA, okay, that's principal axis, is reflected through the focus. Okay, it doesn't matter where this light ray is relative to the to the principal axis. It could even be below the principal axis. Okay, as long as it's running parallel to the principal axis, it'll reflect off the mirror at whatever angle and go through the focus. This is your center of curvature, this is your focus. Okay, so any light ray that is parallel to the principal axis will be reflected through the focus. The next one is a light ray through the center of curvature reflects back on itself. So if I have a light ray coming through the center of curvature here, it won't reflect anywhere else. It'll just reflect back on itself. Okay, we'll go here and back here. Okay. The next one is a light ray that travels through the focus will reflect parallel to the principal axis. So number 3 here is actually the opposite of here, okay, of number 1. Number 3 is if a light ray is passing through the focus, it'll reflect back parallel to the peripheral axis, or to the principal axis. Keep saying peripheral, principal axis. Okay, and the last one is a light ray aimed at the vertex will follow the laws of reflection. Angle of incidence will equal the angle of reflection, similar to the plane mirror. Okay, so if I bounce it right off of this vertex, it'll go right back, following the same the laws of reflection. The principal axis will act as your normal in this case. Okay, there's some really good videos that have been posted on the unit outline, so take a look at those videos as well, okay? There are a number of different cases where we actually are locating objects in a plane mirror. Okay, the first one is objects that are located beyond C, or beyond the center of curvature. Center of curvature is right here, your focus is right here. Okay, this is where the object is past your center of curvature. Okay, so you have your incident light rays coming off of the luminous source, in this case, luminous source. It could be reflected, it could be an arrow, whatever it might be, an object. Okay, and it hits the mirror, and we know that because of rule 1, this is traveling in a parallel fashion to the peripheral axis. Okay, so it's traveling parallel. We know that it's going to pass through F. Okay, we also know that a light ray that passes through F will bounce back and go parallel to the peripheral axis. Okay, so whenever you're drawing an image in a concave mirror, you always have to have one parallel to the peripheral axis, or to the principal axis, and one going through F. Okay, in this case, where an object is passed beyond the point of center of curvature, what's going to happen is these light rays, these incident light rays, are going to go through their given paths, and they're going to be reflected back, given their whatever their path might be. Okay, and they're going to converge past F, in between C and F, to form an upside down inverted image. And if you remember from the plane mirror, we did an acronym called SALT: size, attitude, location, and type. Okay, in this case, it's going to form a smaller than the object, so the image is going to be smaller than the object. The attitude is inverted. Okay, the location is located between C and F, and the type is a real image. The reason why it's a real image compared to when we had a virtual image in the plane mirror is because the image can actually be formed on a screen. So if I had a screen here, okay, if I had a screen right here, what would happen is that these light rays will bounce off the mirror, and actually converge on a screen, and that forms on a screen in front of the mirror, okay, on this side of the mirror, okay, and that creates an inverted image, and that's considered a real image. Okay, and there are some really great videos that go through this and demonstrate this point even further than me just talking. Okay, so go take a look at those. So the size is smaller than the object, the attitude is inverted, the location is located between C and F, okay, and the type is real. Okay, and all you would do to really draw this is you would draw one line that goes parallel to the principal axis, one incident ray going through the focus that reflects back parallel to the principal axis, one line that goes parallel to the peripheral axis through the focus, and right when those two rays converge is where you're going to draw your image, and that's where your image location is going to be. And you can see that between C and F is where that image is located. Okay, this is just a depiction of the virtual image. Okay, if you look at the image here, the reflected rays will never converge on your eyes. Okay, they never converge on your eyes, whereas here they would converge. Okay, and you would see the image right here. Okay, and that's why this is a virtual image, because the reflected rays will not converge from a single point. Okay, so if I were to draw 2 points here, which I did here, they bounce off the mirror and they don't converge. It looks like the image is coming from behind the mirror when in reality it's just reflected that way. Okay, this one would actually form an image on a screen. Okay, case B, object at C. Okay, so this is if I put the object right at the center of curvature, what's going to happen? I draw my parallel to principal axis reflected through F, and then I draw my incident ray going through F parallel to, then bounces and reflects back parallel to principal axis. Okay, and they will converge, both rays, both reflected rays will converge at C. So my salt for this particular image is size, same size as the object. Attitude is inverted. Location, also located at C. And type is a real image. Again, a real image because the light rays converge in front of the mirror. Okay, they converge in front of the mirror. This would be behind the mirror. This is in front of the mirror. Okay, and that's why it's a real image, because if I put a screen here, you'd be able to see this image reflected. Case C, objects located between F and C. Okay, so if I have an object in between my C and F, okay, center of curvature, my focus, again, I'm following the same rules as I just mentioned earlier in this lesson. Okay, parallel to principal axis through F reflected back through parallel to the principal axis, and where these two reflected rays converge, I am getting an image beyond C that is larger than my object. Okay, so I'm looking at my salt here, it's size larger than the object, attitude inverted relative to the object. My location is behind C, as you can see here, and my type is again real. Okay, again, it's real because my reflected rays will actually form an image on a screen if I hold the screen up here. Okay, the next one is if I put an object at F. Okay, if I put an object at F, it doesn't matter where I put that object. Okay, it doesn't matter because it will never form an image. And it's true. If you go too close to, say, your bathroom mirror, the one that you look for, like when you're plucking your eyebrows or something, not that I do that, but if you were to pluck your eyebrows, you go into those really concave mirrors. If you were to stand too at a perfect distance, you wouldn't actually see anything. It'd just be a blurry mess. Okay, you wouldn't see, it'd just be blur. Okay, it's because the light rays don't ever converge. Okay, as you can see, my light rays run parallel here, and they don't converge at the back here. There is one more case, okay, where object is located between F and the mirror. Okay, and this would be the example that you would use for when you are looking in the bathroom concave mirror where you're trying to pluck your eyebrow or whatever, trying to get really, really close. The closer you get to that mirror, the larger your face appears and the bigger your hair follicles appear, and it makes it easier to pluck those one specific hair follicle that you're looking at. Okay, and that's the kind of mirror that you're using here. So for this particular one, you're going as close as possible. So you're between F and the mirror. So you're between the focus and the mirror. Okay, and what happens is, again, you're drawing your light rays, okay, parallel to the principal axis, reflected through F. Okay, and then through F, the light rays come starting out here through F, okay, and bounces back parallel this way. In this case, what's going to happen is you're going to have a size is larger than the object, okay, you can see right here. The attitude is upright and relative to the object. The location appears behind the mirror. Okay, the reason why the location appears behind the mirror is because the reflected rays do not converge in front of the mirror. Okay, the only way is if I extend the rays past the behind the mirror to form this image back here. Oh, that means that the type of image that's being formed is your virtual image because there does not result from the convergence of actual light rays. The real image is the convergence of actual light rays in front of the mirror, but these are light rays that have been extended past the mirror. In your homework, I'll give you a copy of this sheet that's completely filled out. That just goes over again the rules and where the images side, the salt of each one is. So if I have an object beyond C, an object at C, an object between C and F, an object at F, and an object inside of F, what my salt for each one of those is going to be. It's also located in your textbook on page 499. Okay. A good resource to go back to is to read pages 496 to 499, or so for 500. And take a look at that, and that might help you out a little bit more as well. Okay, guys, thanks.